Okay, so good afternoon, everyone. So we have already, you have already seen that how we can able to form the spectral element matrices for the bar, beam. Then we have went for the frame element. Then we have also shown some of the thin wall beam and like this thing. So if you see, like if I just go back, so this thing we have actually completed, like the frame element, which is consist of the bar and the beam element. Then we have we have calculated the full thing. Then we have went to the frame element. No, yeah, that frame element. So yeah, after that we have went to the 3D frame element, 2D, then 3D frame element. So in those cases we can see that the number of degree of freedoms are increasing a lot, and the prime point is that we have to find out what is the solution for the displacement field in terms of the unknowns. So once we can able to express in terms of the unknown, we are assuming that solutions are like in the time domain they are the harmonic solutions, so we can able to substitute them and we can express the full thing in the frequency domain, and we can find it out what are the governing differential equation, and from there we can able to solve it. So these are the monosymmetric like the thin wall monosymmetric beam, and then we have the frame elements we can able to get. So you see like that once we are doing for the thin wall monosymmetric beam, we can get the eighth order differential equation, and once we solve that eighth order differential equation, so we can able to get like this way. And all the cases we have to do like this. We are expressing the displacement fields in one side, unknowns with the matrices, and other cases force, again the transfer matrix with the unknown. Now our strategy is we are calculating A from here, so A equal to B inverse D and V inverse D, and we are substituting that V inverse D here in place of A, and we will get that the F. So H into B inverse is basically our spectral matrix, and that spectral matrix is also dependent on the frequencies. Okay, I think we got the point how this thing is happening. Now we can see that in these throughout the cases there was one primary point, that once we are making this differential equation, in that case the coefficients are not dependent on y. That's a very important point. They are the constant coefficient. Constant coefficient. So once the solution is constant coefficient, then what happened? Then these approximation we can able to do, like this approximation, that is like h of y equal to summation of like ai e to the power of lambda I y, that is valid once we are having the constant coefficient. Like this theta 1 is a constant term. You see, for a beam that is not going to change. For any particular beam that is not going to change. That is not going to change. So they are not going to change actually through the y. Like throughout the domain they are not changing. So therefore these are the constant coefficients. They are the constant coefficients. So with the constant coefficient we can easily able to solve the thing, assuming the solution like this. But what happens if the cross section or something is changing with the domain? For example, the tapered beam. If we take the tapered beam, what will happen here? So if you see the normal beam equation, that was ei del 4w del x4 plus rho a del 2w del t2 equal to 0. But now here if you see what exactly happening, I, which is the moment of inertia or the second moment of area, that actually get changed with respect to the space. So as far as we are going in the x along the height, our I get changed. Now that's create a big problem, because now the coefficient is not a constant coefficient. So if we see that, if we try to write down the equations little bit like polished manner, like suppose if we're just expressing something like Rx that is equal to So at any particular height, if we try to write what is the radius, we can say this is the radius, that rs plus re minus rs. So rs is the bottom one and re is the top one, so re minus rs, and that is equal to this. So c is like the variation, that how much variation it is happening. Then ax, that is basically we can get in that same manner, like 2 pi r into tau, we can get this way. Then ix equal to this. So now if we substitute that all those things, so ix, ax, if we substitute, we can get this expression. And more importantly, here you see that this term is not a constant term. This is with x, where x is the domain. So our coefficient is not constant. So how we can do that? So we have this thing. So in this case, actually, so previously if it was, we can write it simply like w of x, we can write it summation of e to the power of lambda ix into, or maybe lambda aj into aj. But here you see, instead of e to the power lambda jx, we have to write it phi jx. That's the problem. Now this thing is not known to us, because now coefficients are not constant, they are dependent on the x. So we cannot write it like that way. And if we are expanding that, we can write the three terms, you can see here. So they have all have the means, all or maybe few have the term of x inside. So you can get it like that. So coefficient, so here actually there is a very powerful technique we can actually able to use to solve that. That is, we can use the series expansion. So what we can do? We can actually expand this thing with the coefficient of power of x, and we can get in this way these terms. So what basically people are doing here? So yeah, so our target is what? Our target is to calculate the phi jx, because now phi jx is not known to us. We try to find it out. So what we can do? So we are writing it in this form, that we are trying to solve this problem, we have to first assume the solution like this. Here there is a small difference with this previous. If you see here, we are going only the four terms, a1, a2, a3, a4, done, and there is a phi, some complicated function of x. But how we are writing that function? We are not writing that way. We are writing it w of x, that is equal to summation of an x to the power n. So if I just write it down, it will be becoming a0 plus a1x plus a2x square plus a3x cube plus a4x to the power 4, a5x to the power 5, like this way it is going. So here we see we are taking much more term, not only up to 4, we are taking long more terms. And also if you, so that is not exactly equal to phi j xj aj, no, we are taking like this way. After that, if we do the derivative, what will happen? dw dx, simple thing, a0 will be vanish, because a0 is a constant, it will vanish. So we will have a1 plus 2a2x plus 3 a3x square plus 4a4x cube, like this. So what can I say? This is n into an x to the power n minus 1. Agreed? That's the first order derivative. So what is the second order derivative? Second order derivative will be this, third order derivative will be this, fourth order derivative will be this. Okay? Agreed? Okay, very good. Now what was my equation of motion? My equation of motion is like this. Okay. So now if you start putting each and every terms there, what will happen? Like let's say you put that A4, you put it here. Then second term, so first term with that A4 term, so sorry, W4 term, so you put it here. So it will start from where? It will start from A4 something plus something A5 plus something A6, like this way. This term will start from A3 something. This term will start from A2. This will start from A1. Okay. So you can substitute all those terms here. Agreed? So what will happen? We can get some coefficient with A1, some coefficient with A2, some coefficient with some coefficient with A0 also, like this way we can get. Agreed? Okay. So that exactly what we are doing here. So let's try to see what happening with the term where x0 is actually occurred, means x to the power 0 means the constant term. So let's see how the constant terms looks like. If we can understand how the constant term is coming, we can also able to calculate the all other things. Okay, so let's try to see. So wx, if we put it here, we can see that what is the constant term? A0. So the term is coming minus eta square A0. Agreed? That will be my constant term. Agreed? Yeah, other terms are also there. I'm not talking about that other terms. I'm just talking about the constant term first. Constant term will be this. Now think what happened with the constant term of this. That one will be coming from here. That means constant term is A2. Okay. So if I substitute it here, this one will become 6 square into A2. That will be my constant term. There will be other term, definitely. But constant term will be 6 square into A2. Okay. Then if I substitute this one here, then my constant term will be, I think I made a small mistake. That is not only A2. This will be A2, 2 into 1, so 2A2. That will be 12 actually. So now if I put this term here, then constant term will be how much? That will be 2A2. My constant term will be how much? That will be 3. So 3 into 2 into 1. So that is actually 3 factorial, but 6. 6A3. So 6A3 will be coming here. So it will become 6C into 1 plus Cx into 6A3. That will be my. Yes, here again we have to see that once we are getting this term, so what is the term for the x? So x term is only because that term has x, so I am forgetting that one. So what with the constant term? So constant term will be 36 Ca3. That is the constant term. Just giving it out. So 36 Ca3 is the constant term. Agreed? Then if we put it here, what we can get? That is 1 plus c x square. So I can write it 1 plus 2cx plus c square x square. So 1 is only the term with which it will be multiplying, and here it will be 4. It's coming like 4 into 3 into 2. Okay. So 4 into 3 into 2 is how much? 24. So that is 24 into A4. So what is my all constant terms? So my constant terms are minus n square A0 plus 12c square S2 plus 36 CA3 plus 24 A4, that is equal to how much? that should be equal to 0. So that full equation is equal to 0. What I try to do? I try to expand the full thing in terms of the x, power of the x, and I try to calculate all the coefficients and I try to substitute them. Okay, so what happened? Constant term, whatever, plus something into x, plus something into x square, plus something into x cube. That way the full thing is coming in the left hand side, and that is equal to right hand side equal to 0. So what can we say? If that full polynomial equal to 0, each and every term of that polynomial or all the coefficients of that polynomial has to be 0, because it is solving for all the x. So once that is satisfying, what can we say from that? We are getting one equation like this, that this is equal to 0. You can see exactly here what I have done. You see the coefficient of power of x. I just try to calculate it. So first for 0, I put 24 a4, 36 c3, 12 c square and this. Then for the x, so that is constant term. This is x, this is x square, this is x cube, x to the power 4, like this way. We can do the full accounting actually. Then we can get all those terms. Now here there is a very important point. So what happened? The summation of this full thing should be equal to 0, and that's become one of my equations. Now think, how many a we need? How many a do we need? 4. A1, A2, A3, A4. That's all. We don't need anything else. Okay. So from here, what can we do? Now we can start back substituting. So we can start writing that once we get this, we can write that A4 is equal to this. So we just start writing everything in terms of the A0, A1, A2, A3. Agreed? So I can first try to express what is the A4. A4 in terms of A0, A1 is not there, okay, doesn't matter. A2 and A3. Then next case, A5. So in that expression of A5, I can substitute whatever is the A4, I can substitute it there. Because you see, A5 equation, here take a look, it is always going down and it is starting from A5. So our target is to solve for this first one. So this row will give me A5, this column will give me A6, then next one I will get A7, A8, like this one. That's the full series we can able to solve. That benefit is also phenomenal. You can just able to get a expression for a conical beam. Otherwise, what you have to do, you have to do it finite element meshing, like small pieces, do the convergence test, check how it is coming and not, and maybe you cannot able to get some analytical version of it. So here this allows you to get a direct analytical version. So obviously for that, if you want to get some very good output, you have to bear with the pain. That's nothing to do. So yeah, so this thing is coming here, and we can able to, and these actually makes a full sequence, and you can see that you can actually able to evaluate some sort of expressions like this, that a n equal to, like this way we can able to get that, and we can just substitute that and we can able to get what are the different ans we can getting. After that, what we can do, now we can start putting all those things together, that is a0 with this, a1 with this, a2 with this, a3 with this. So we got that. The question comes, how do we can solve? A1, A2, A3, A4, A5, all those things we can get. Fine. Now, what was our main equation? We assume this one as a solution. Now we have to convert it back. So like here, A0 plus A2, A3, A4. So now we have seen that what are the parameters like A1. Now we are started getting like now my A4, I can now able to express A4 in terms of A0, A1, A2, A3, A5 in that term, A6 in that term. Agreed? Now from all these, if I try to collect what is my coefficient of the A0, what is my coefficient of the A1, what is the coefficient of the A2, what is the coefficient of the A3, can I able to write that full thing in this form? Because here if you see this form ask me to write it phi1 x A1 plus phi2 x A2 plus phi3 x A3 plus phi4 x A4, that is being asked. And I try to write all the different A1, A2, A3, A4, A5, A6 all in terms of A0, A1, A2, A3. So whatever the coefficients are there, all is expressed in terms of the first four variables. Agreed? Agreed? There all the x square, x cube, whatever the polynomial of the x, all are punched into it. So now the coefficient of each of the parameter like unknowns is in the function of x. So that way we can able to get in this form. This is my phi1x, phi0x, phi1x, phi2x and phi3x. Now good point is that this phi, whatever we are getting for the conical section, this is close to the Bessel function. This can be represented as the Bessel function. So we are just writing it in terms of the Bessel function. A is basically some form of x. Some sort of way the x can be written. So that I think that is this 1 plus cx, something like that. A is something like that. So again you see we are writing it in that way, that R into E. How, where we have written R into A? If you go back to the thin wall, you see how we have written the displacement field, that R into A. So we again go back to there. Just now here our coefficient means the, what to say, the functions are no longer only to the power of lambda x. Now they are become power series or something. And here you can see that becomes like a Bessel functions. Okay. Quite problematic thing, but it doesn't matter. Okay. So after that, what we can do? So once we have written that W in this form, then from here we can calculate the phi. What is phi? Del W del x. Then again moment EI del 2W del x2. Then shear force EI del 3W del x3. You can calculate that. Okay. So we can get it like phi RV, phi M, phi. Again from there I can write it D, B, C. Same thing. This portion is very simple. So with this, what we have covered, we have seen that first, if the coefficients of the equations are constant, this is very simple thing. We can just directly get e to the power of lambda x t. Done. Whatever the order of differential equation, we can just substitute it and simple manner we can formulate the full thing. Very simple. But if the coefficients of the differential equation are no longer constant and they are variable with the domain, then it creates a bigger problem, and there we have to do like this type of crazy things. Sine, cosine, so many things, that series expansion, so many crazy stuffs has to be done. Now, some of the time, this thing may be much more difficult. Even some of the problem could not be able to solve accurately. For example, here you see this is a conical. So we can nicely write this way. Okay. But think you have a beam where the, like, if I draw it in that way, and this is sine of some variable, maybe not maybe c into x. Like it's become like a pipa, a barrel. You think it like a barrel that go up like a sine function. Once it is moving, it's like a sine function, or like something plus some sign, that also possible. You may add some constant term, maybe c0. So that's constant. It goes some constant and then like a sine, full thing. In those cases, it's become much more problematic. Why? Why it will become problematic? Because once we will try to resolve it, we can get this type of equation. Fine. After that, this coefficient matching will not be possible because you will have sine, cosine here. Now you cannot make the sign in terms of again you have to expand the sign also, then you cannot able to solve it. Actually, there actually those cases you will face some difficulty. There you may need to come up with some specific type of the solution technique. Okay, and these are very advanced, very advanced, literally. Maybe in research, maybe you can, if you encounter with something like this type of problem, maybe you can try to solve it. Okay, you can get that derivation and all those things in the book also. So with this, we can conclude this here.